Hi everyone, I'm Frederick, and my colleague Carlo Giacometti and I are going to be talking about speech and speaker analysis today. All right, so it's useful to model speech as a source and a filter, where the vocal fold vibrations from the resonator source are filtered by the vocal tract. Rather than operate on the entire signal at once, we like to partition the signal into frames and multiply by a smoothing window to reduce artifacts from the frame boundaries. We can compute the discrete Fourier transform of each frame and take the squared magnitude. That gives us the power spectrum, which shows the evolution of the frequency energy distribution over time. Just as a quick example, this is a speech signal, it's time domain and spectral representation.
Turn up the volume.
Sure.
Just
Oh, okay. Sorry. Is this better? Oh, okay. Sorry. All right. So for many classical approaches, we don't stop at the spectrogram, but we go on to compute a variety of speech and speaker-dependent features. So formants are concentrations of energy around specific resonance frequencies in the vocal tract, and their relative shape and spacing is intrinsic to different phonemes and rather independent of the pitch of the speech, which would depend on a specific speaker. It's easily accessible through audio local measurements, and here I'm showing the formants computed over 5 frequency bands against the spectrogram. I've just masked the soft version of the section of the input to make the display cleaner. Another speaker-independent feature is the MFCC, or the cepstral representation. It's a low dimensionality feature, primarily speaker-independent, as I said. We start out with the power spectrum, and for each frame in that spectrum, we filter it using a non-linearly spaced filter bank to approximate the frequency response of human hearing. We normally use the log of that to model our decreased sensitivity to higher frequencies. And we take this smoothed, warped spectrogram and take the inverse Fourier transform to get a set of uncorrelated coefficients where most of the speaker-dependent pitch information is removed. And basically this leaves us with a small set of features which contain semantically meaningful information about the input. And this is also easily accessible through the audio net encoders and audio local measurements. I'm going to take a brief interlude and talk about preprocessing. So in the wild, many signals are noisy, and this can adversely affect the features and their ability to model an input. So various ways to combat this are with cepstral mean subtraction. We can also normalize the mean and variance of the cepstrum with respect to either a single example or an entire data set. We can also normalize the amplitude of the input. It's also helpful to remove speaker-dependent information like the pitch. For example, we can apply vocal tract length normalization. Basically, we scale the frequency axis. Here, if you randomly perturb the amount that you're warping this axis, you can use this as a neat data augmentation for neural net inputs. We can also boost the high frequency component, which is pre-emphasis filtering. That brings out the higher formants. Voice activity detection is the task of segmenting an input into speech and non-speech components. It's a challenging task in and of itself, but it's also valuable as part of the preprocessing pipeline. For example, the cepstral subtraction depends on having an estimate of the background noise, which you would use a voice activity detector to find those background frames and then compute the statistics on them. It's also a prerequisite for the diarization task, which is labeling an input based on who spoke when. So you have to know when in the signal the speech is actually occurring first. So classically, this is done by using a Gaussian mixture model with an estimate of two distributions for speech and non-speech. And normally a hidden Markov model is added on the end to smooth the decision history. There are also neural net-based methods. And we're planning to expose these in 12.1 through audio intervals and audio local measurements. So here I'm just showing the waveform with the detected voice intervals. So back to features. There are a couple of speech parameters that we use for synthesis. We're using the world library to extract these features and perform the synthesis. And it generates a high-quality synthesis, and it's pretty efficient for real-time processing. So first, there's the fundamental frequency, or the pitch of the speech. There are many methods for computing this. The vocoder method it operates on the waveform and uses a bank of bandpass filters and basically correlates that with the input and generates some frequency candidates and chooses a smooth path through them. And this is available through audio local measurements. So here's a plot of the detected pitch over time. The spectral envelope contains information about the filter response of the vocal tract, which determines the formants independently of the pitch of the speech. The world library uses a version of the Cepstrum, and they have an interesting strategy where they specially construct windows for each frequency band to reduce the harmonic interference there, and they additionally filter the spectrum to reduce ripple from the initial windowing. And here's what the spectral envelope looks like. Finally, there's the aperiodicity component. The quality of synthesized speech can be improved by adding an estimate of noise from aspiration and fricative sounds and combining that with the source generated by the vocal tract resonances. And the world library expresses band aperiodicity as a ratio of total power to power of a sine wave fit to each frequency band that it's analyzed over. That's what this looks like. You can see it kind of lines up with the high frequency, noisy areas of the spectrogram. So several methods exist for synthesizing speech. Our vocoder uses a source filter-based method and basically convolves the periodic component of the signal along with the filter response, or along with the excitation signal, which is it computes that from the free 3 parameters I just mentioned earlier. There are also neural net-based methods for synthesis, which we'll hopefully look into adding in the future. So here's a quick example. I'm going to initialize the world library with a window size and an offset, perform analysis on the input signal, and collect the fundamental frequency, spectral envelope, and aperiodicity. And I can synthesize this with the original parameters.
Right then. Perfect timing.
I can also modify the fundamental frequency. So here I'm pitch shifting by an octave.
Right then. Perfect timing.
So audio pitch shift kind of takes a more naive approach and just scales the frequency. So you kind of get a chipmunk effect.
Right then. Perfect timing.
So this occurs because the spectral envelope and therefore the formants also get shifted when you just scale the frequency. And the vocoder method avoids that by keeping the spectral envelope constant while only modifying the fundamental frequency. We can also play around with the aperiodicity component here. I'm just fixing it at 1.
Right then. Perfect timing.
There are obviously much more interesting things that you can do with that. You can also define a backward transformation between like a reference and a target parameters and kind of morph between them. Just another interesting thing to do. Right. So in 12.1, we're augmenting some existing audio processing functions with speech-specific methods. So here the speech method of audio time stretch is going to use the vocoder to do the synthesis, whereas the automatic method will just use the time domain overlap add.
Right then. Perfect timing. Right then. Perfect timing.
So it sounds a bit better. I already gave an example of the pitch shifting. Also, the pitch recognize will also have a speech method which uses the fundamental frequency detection algorithm from our vocoder library. We also have and are adding some more functions for high-level speech understanding. So in 12.0, we introduced functionality for transcribing spoken inputs. This is speech recognized. It's trained on the deep speech 2, or it uses the deep speech 2 network, which was trained with a CTC loss. Here's an intermediate decoding from the result of the net, where we have the character sequence on this axis, and here we just have a decoding derived from the maximum probability character at each time step. And for in-speech recognize, we chop off the decoder in the network and allow a character level language model to then adjust the probabilities before exploring the output space with a beam search. And that kind of helps correct spelling errors. So in 12.1, we're also adding speech cases as an analog to text casage, which allows you to extract computable data from a recorded input.
I took a plane from Chicago to London, then I took a train to Berlin in Germany.
And then, I don't know where my input went. Sorry, there we go. We're also introducing speech interpreter to make speech immediately interactive and accessible. So, for example,
8 squared.
Is identified as 64.
7 squared.
That's not an even number. And so now I'm going to hand the talk over to my colleague to speak about some more neural net-based applications.
Okay, and I will be focusing more on speaker analysis and the work that we have been doing. You have a quick question while we're changing computers?
Yeah, how diverse is the phonetic library? Like, are you doing like all the rolling R varieties, like U or R?
So all of this, all of the stuff that you have seen, like for the speech recognition, that never touches the phoneme level. That is an end-to-end trained neural network. So it goes directly from audio to a sequence of characters, not phonemes or phonetic representation. So it's a fully end-to-end approach to that problem. Well, that is limited, right, by the training data that was used for the speech recognition. In general, that is pretty robust to that kind of thing. In terms of synthesis, just a second, give me a second to figure out what cable I need to attach. In terms of synthesis, we haven't done very much in terms of, we don't have yet neural network-based synthesis. In that case, it will also be an end-to-end kind of process. So I will switch topics, slightly at least. I will talk about speaker analysis and what the motivation for it is and what we have done and which directions we are investigating. Of course, absolutely. Is this more appropriate? Excellent. So what we want to have is something similar to what we have for Audio Identify, which provides a two-tier service. One is kind of silly. You have a signal, which I will have to pipe to my output device. Then hopefully everyone will be able to hear it. Excellent. And it tells me, oh, it's music, fine. This is kind of trivial, not particularly interesting. The real interesting thing is that by modifying the network that, on which this is based, we get a feature vector per each of our input signals. And this makes the audio object an easily computable object. So you can easily compute distances, for example, between signals or visualize them in a semantically relevant space. So we want to do the same, but something that understands voices and speakers rather than is it music or is it a car crossing the road or something. So we used a publicly available dataset, which is called Voxelab2. It's about 1 million samples collected through YouTube from about 6,000 celebrities, or whatever passes for celebrities. Each signal is labeled with the main speaker. Of course, tagging is done in a kind of an automated way, so there is label noise. So data isn't particularly great, but there is a lot of it, essentially. This is the short story. What have we done to recognize these speakers? What have we used? Well, first of all, we want to encode our input into a spectrogram. And this is our example data.
Right then. Perfect timing.
That Rebecca has already played. And we just do a computer spectrum over it. We discard a minimal amount of information. We wouldn't use something like MFCC features, because that tends to lose the information about the speakers, which is exactly what we are trying to retrieve here. So this tensor then is, can we do questions later, sorry. This tensor is then fed into a network that was inspired by the VGG network. It's just a bunch of convolutional layers that are fed into each other with nonlinearity in the middle. This is a temporary result. We will try to train slightly more complicated networks. This doesn't give optimal results yet. And of course, the name that I am reporting here is even more temporary. And you can see I just throw a recording our example data. I throw it onto the network, and I get a classification result, whoever Liam Neeson is. It's kind of the boring part. Now, one quick interesting thing about the network, as I said, it's a stack of convolutions. Now, there is some kind of finesse to make these work in the Wolfram language with variable length data. If you just do what you would do for images, just say, I want a convolution applied to my input encoder, that fails miserably because we expect a rank 3 tensor. So you could reshape your input. But that would also fail because the encoder produces data that has a variable dimension on the first dimension, with which the neural network framework is most definitely not happy. So to make this work, we use the interleaving option in convolution layers and batch normalization layers, and et cetera, to make sure that the convolution is applied to the time and frequency dimension, not to the frequency and channels dimension, for example. Anyways, we construct a stack of these, and then we end up with this variable length sequence of matrices. We want a single result, so we want to aggregate this result over the time dimension, and then use a normal classification stack. As I said, this produces a variable length output, and we just use an aggregation layer to collapse the time dimension of our signal, and then we are allowed to perform a single classification for a variable length signal. So this network was trained. We get reasonably decent accuracies. The top 3 accuracy is 85%. Of course, as I said, this is work in progress. We are planning to test different kind of architectures. But this is already a kind of okay-ish result, let's say. So now the interesting part, as I was saying, is to modify this network to finally get features that are semantically significant in the space of different speakers. So as an example of this, I have a bunch of recordings from different speakers, and they say different things, right? But what we want to see is a feature space plot of this computed using the network that we have trained. And you can see how different speakers are separated in different parts of their feature space, even though the network had never been exposed to these specific speakers. So one thing that was added in addition to this after the classification training, we fine-tuned the network. And the goal here is not to perform a classification, but to optimize the embedding. so that different speakers will be clustered in different parts of this 1,000 or so dimensional space where the features live. And there are several strategies that one could use. I listed here some with references. I will give, we use a distance-based loss in our last training. We are planning to use the arc phase in the next one. I will give a minimal example with the contrastive loss. So here we define a simple recurrent network for classification. And we train this network on a tiny dataset with speech from 5 different speakers. I will not run the training right now because we are very short on time. And then we chop the network so we have something that extracts features. In this case, I added a bottleneck layer in the network that produces something with dimension 2. So we can visualize the actual output of the embedding rather than something that is then further reduced in dimensionality. So this plot is directly the plot of the output of the network. And you can achieve very good separation like this already. Now, what we can do to improve the situation is to do contrastive loss training. So the idea is that you feed this network with pairs of inputs, and you want the embeddings for these pairs of inputs to be closer if they belong to the same class, or further away if they belong to different classes. You do this, here I am just taking the network that I have already trained, inserting in a graph that has 2 inputs, and I make sure that these 2 copies of the net share the parameters, so that the training happens synchronously in both of them. And I use the contrastive loss layers, as I said, which minimizes the distance if they belong to the same class and maximizes if they belong to different classes. And you can see that we did further separate the clusters in the feature space. As I was saying, we are doing the same kind of thing. This training that I'm showing here use a distance-based loss. We are planning to investigate other strategies. And you can see that the same example that we were looking at before has better separation of classes in the simple example. The nice thing about using a convolutional net for this is that we can get a time-resolved version of the features, which gives us a foothold onto the speaker diarization problem, which is, given a single recording, we want to know who spoke when. Of course, if we get only one feature vector per recording, this clearly has no hope of working. But if we return a sequence of features, we can try to cluster it. Here I have
Good evening from Washington University in St. Louis, Missouri. I'm
some presidential debates some years ago. And I compute the time-resolved features with the net that was trained, and then run find clusters on it, and then plot the result. And you can see how I can recognize different clusters in the feature space that correspond to different intervals in my signal. So now, as for the functionality that will come out of all of this exploration, I'll quickly touch this. So the first thing that we want to add is a named classifier, which will be the notable speaker classifier. Hello, this is a test. And this works like the notable person classifier for images. Well, at least it's supposed to work. I have no idea who this is. Excellent. Thank you very much. I see. So this clearly is not something that is of crucial importance. The main thing is that we have this way of representing audio signals in a semantically meaningful feature space. So all of these features will be available in all of the machine learning functions. So you'll be able to say feature space plot of some audio signals and specify that you want to extract speaker features, and without any other input from the user, you will be able to produce something that is aware of voices. The last 2 functions that I will just mention are speaker match queue. Very simply, we have two inputs, compute the features for both inputs, measure a distance, and then have a probabilistic estimate if these features belong to the same or different speakers. And finally, speaker recognize, where the idea is that you will be able to provide a small data set of examples, labeled examples from various speakers, and this will allow you to then recognize from an unseen example what is the speaker from this unseen example, if it matches any of the speakers that were present in your small training set. And with that, I think I need to finish because Giulio needs to start the next talk very soon. Maybe you